Good morning, dear students. My name is Ferhan Mazher, and today is 20th of the March 2022. Right now, I am with the 11 Cambridge class. Today is Sunday, and the subject we are studying is Physics 5054. Today, we have set our hearts to solve a theory paper, and we have selected October, November 2014 2 paper. This theory paper, this paper 2 belongs from the zone 2, or you can say it belongs from the variant 2. We have already worked on this paper and I have already made a video on it, and in that video we have done the section A of this paper. Today in this session, in this video, we are going to do the section B of this paper, and this section B has 3 questions and we will attempt all of them. So without any ado, let's start the today's paper. So on your screen, here comes the paper. So this is October, November 2014 2 paper, theory paper, and the section B of this paper is showing up on your screen. The question is, what is meant by the uniform acceleration? Uniform acceleration means that there is a body is moving and there is an equal change in its velocity in equal intervals of time. If the change in the velocity in equal intervals of time is constant, we say the body is moving with the uniform acceleration. So that is my answer. So let me show you the answer which we got. Question number 9. We are going to question number 9. Sorry for this. Okay, so question number 8. Here we go. So equal change in the velocity in equal intervals of time, body is said to be moving with the uniform acceleration. So I hope you understand. Okay, so let's see what's the next part. The B part is, he says, acceleration is a vector quantity. State how a vector quantity differs from a scalar quantity. You see, the vector quantities are described completely by direction and magnitude, but the scalar quantities are only described completely by their magnitude. So the vector quantities have direction, but the scalar quantities don't have direction. Okay, so here we go. Vector quantities have both. The vector quantities have both direction and magnitude. Scalars have only magnitude. Okay, so let's see what's the next question. He says, okay, so here we go. He says a rock from space is traveling in a straight line at high speed when it enters the Earth's atmosphere. Figure 9.1 is the speed time graph for the rock for time t0 to time 50 seconds. So here you can see the rock is moving with a constant speed up till 10 seconds. Then it started decelerating. Here the deceleration is non-uniform. Here the deceleration is uniform. Here the deceleration is non-uniform. Here all of the sudden the speed of the rock has become 0. It means the rock has hit the ground. It's a speed time graph. Here the speed is represented on the y-axis, and here on the x-axis the time is represented. So their first question coming up on your screen, he says, on the figure 9.1, mark a letter X where the rock is moving with a constant speed. A letter Y where the rock has a uniform deceleration. A letter Z where the rock has a non-uniform deceleration. So let me show you. I have done this already. So let me show you. So clearly you can see here the rock is moving with the constant with the 0 acceleration with a constant speed. Let me check what was their question. Their question was where the rock is moving with a constant speed. Yeah, we are right. So here the rock is decelerating with constant deceleration. and here is non-uniform deceleration. So X, Y, and Z. Hopefully you understand. So then he says at the time t equals to 25 seconds, the mass of the rock is 8.4 kg. For the time t equals to 25 seconds, determine the size of the acceleration of the rock. Okay. So at time t 25, so it will be here. Time 25 is here. You see here. So from here to here, it's a straight line. So I will find the gradient of this straight line, and that will be equals to the value of the deceleration, or you can say acceleration. So let me show you. So I have taken 2 points on that graph. One point is 20,99600, and the other point is 30,4500. I will find the gradient of this straight line, and that will be equals to the acceleration there. So it will be 4500 minus 9600 and divided by 30 minus 20. So 5100 divided by 10 and equal to be 510 meter per second square. I have just ignored the negative sign, which I just got from here, because you can write that negative sign. Let me write that negative sign also. So you should know that we are here, we have a negative sign, because this actually this is a deceleration. Okay. So you can write it, or if you don't want to write even then it's right. So the value of the acceleration here is minus 500 meter per second square. Hopefully you understand. So let me check. Then the question is that the size of the resultant force on the rock. You see, if I know the deceleration produced in the rock, I know the mass of the rock, I can also calculate the force which produces that deceleration. According to the Newton's second law of motion, F is equals to ma. So F, I want to find out. Mass is 8.4 kg, and acceleration we have already calculated. So very easy and simple numerical, this one. Okay, so here we go. F is equals to ma 8.4 kg multiply 500 Newton, so 500 meter per second square. So the answer will be 4200 Newton. So the resultant force acting on the body is 4200 Newton. So let's move to the next part. He says figure 9.2 shows the rock. He says the figure 9.2 shows the rock at t equals to 25 seconds. So here is that rock which is coming out of space and is coming towards the earth. So this is showing the earth. The direction of the travel of the rock is this, and this is the surface of the rock. On the figure 9.2, draw and label 2 arrows to show the direction of the gravitational force F and the air resistance R acting on the rock. You know, the air resistance R will be opposite to the motion. So because the rock is moving in this direction, the air resistance will be opposite to the motion. So because the rock is moving in this direction, so the air resistance will be opposite to this, exactly on the same line, but in opposite direction. And the weight will be towards the surface of the earth. The weight will be towards the surface of the earth. Here you can draw a tangent, and it should be normal to this surface. The weight is always towards the center of the earth. So I will draw a line like this, which will make 90-degree angle with the surface of the earth. So let me show you. I have done this. Okay. So here you can see I have tried to draw this. This is the air resistance, and it is opposite to the direction of the travel, and the air resistance is always opposite to the direction of the travel, and the weight is towards the center of the earth. So this is the weight, which is F basically, which was supposed to be represented with the F. Air resistance was supposed to be represented with the R. Hopefully you understand. Okay, so the next part is, he says, suggest why the size of the air resistance changes as the rock travels through the Earth's atmosphere. You see, as the rock will travel through the Earth's atmosphere, the speed of the rock is changing, because the air resistance, one factor on which the air resistance experienced by a body depends is the speed of the body. So because the speed of the rock when it enters into the atmosphere of the earth, that is continuously changing. So the air resistance experienced by the rock, that will also be changing. So let me show you my written answer. I hope you understand my description. And here we go. Speed of the rock. The speed of the rock changes. Air resistance depends on the speed of the rock. Because the speed of the rock is changing, that's why the air resistance experienced by the rock, that will be changing. So let me go to the next question. He says, suggest what happens to the rock at t equals to 40 seconds. So what happened here at t equals to 40 seconds, you see the speed of the rock from 2000 meter per second, all of a sudden it becomes 0 meter per second. The reason I think is, the most probable reason is that the rock has hit the ground. That's why its speed has all of a sudden become 0. So our written answer is the rock hit the ground. That's why at t equals to 40 seconds, the speed all of a sudden immediately has become 0. So hopefully you understand. So we are done with the question number 9. So let's open the marking scheme. So here is the marking scheme showing up on your screen. So I have already checked my answers with the marking scheme, and you can pause the video and you can take your time and read this marking scheme carefully. I can tell you that our answers are right, and I have already checked it, but the marking scheme is coming up on your screen. You can stop the video, you can pause the video, and you can take your time and read this marking scheme carefully. And I always tell you that the reading the marking scheme and checking your answer, your teacher's answer, red spots answer, the answers written by your friends, compare those answers with the marking schemes. And we have also made a rule that we in physics of O-level physics, we never attempt any question whose marking scheme we don't have, because it's very important to check the markings, your answer with the marking scheme. Okay, so let's move to the next question. The next question coming up on your screen. He says, state the speed of the light in the air. The speed of the light in the air is 3 × 8 meter per second. Remember this word, this number. This number you have to remember. This number has been tested many times. What speed of the light in the air? That is 3 × 8 meter per second. So remember this. Okay, so let me show you. So the speed is 3 × 8 meter per second. So here we go. The answer is right. Okay. Okay, so we are going to the next question. He says B part. Figure 10.1 shows a ray of blue light passing from air into a glass block and refracting at the surface. As the light enters the glass, state what happens to the speed of the light, the frequency of the light, and the wavelength of the light. You see, the light is, let me reduce the size so I can see the whole thing together. Okay, you see, as the light, the blue light is traveling in the air. When it will enter into the glass, it will enter into the dense medium. The speed of the light in the dense medium decreases. So what happens with the speed of the light? It decreases. What happens with the frequency of the light? The frequency of the light do not change. And what happens with the wavelength of the light? Whatever happens with the speed of the light, same thing will happen with the wavelength of the light. So when the light will enter into the glass, if from air, from rare medium, it will enter into a dense medium, its speed will decrease, its wavelength will decrease, but the frequency will remain unchanged. So hopefully you understand. Let me show you the answers which we have written, and here we go. So the speed of the light will decrease, the frequency will be unchanged, and the wavelength of the light will decrease. Okay, so we are going to the next part. He says on the figure. He says on the figure. On the figure 10.1, mark and label the angle of incidence I and the angle of refraction R. You see, the angle of incidence is this. This is the angle of incidence, and this is the angle of refraction. So let me show you. Okay. So you can see this, I have done this. This is the angle of incidence here. The angle of incidence is the angle between the normal and the incident ray, and angle of refraction is the angle between the refracted ray and the normal. So this is angle I, this is angle R. Hopefully you understand. Okay. So decrease, no change, decrease, I correctly marked, R correctly marked. Okay, so our answers are right. Okay, so the next part. The refractive index of the glass for the blue light is 1.5. A ray of blue light strikes the surface of a glass block at an angle of incidence of 89 degrees. Calculate the angle of refraction of the light in the glass block. You remember the formula for the refractive index of the glass is N equals to sine I divided by sine R. N is equals to sine I divided by sine R, where the I is 89 degrees, the refractive index represented with the N is 1.5. So we will have 1.5 equals to sine 89 divided by sine R. Sine R will be equals to sine 89, the whole thing divided by 1.5. So R will be equals to sine inverse of 0.67, and the R will be 42 degrees. So that's the answer. The angle of refraction will be. So here we go. So let's have a look at them. That was a 3 marks numerical, very easy and simple numerical. So 42 is the right answer, sir. Our answers are right. Okay. So let's move to the next part. He says, explain why the angle of refraction of the blue light in the glass is always less than 45. You see, when the angle of incidence is, try to understand, it's difficult to answer. This thing is a little bit difficult. When you entered into the glass by making an angle of incidence 89, the angle of refraction was 42. So if you increase further the angle of incidence, the angle of refraction is supposed to increase. But when you make the angle 90, 89, and your angle of incidence is 89. If you make it 1 degree more, the angle of incidence will become 90 degree. And the light will be traveling along the normal to the surface. And when the light travels along the normal to the surface, no refraction takes place. The light enters into the glass without any deviation. We do not change its path. So the maximum angle of refraction can be 42. For the angle of incidence in the 8 is 89. If you increase the angle of incidence further, the angle of refraction will become 0, not 45. So I cannot be more than 90 degree. For I equals to 89, R is 42. So the angle of refraction cannot be greater than 45, is not possible. Because if you take the angle R as 45 and you do the reverse calculation, you try to find out the angle of incidence, it will become 90. And the angle of incidence cannot be 90. Because when the angle of incidence will be 90, the light will not deviate. There will be no refraction taking place. There will be no angle of refraction. The light will not deviate. A little tricky answer. So look at here on the marking scheme. He says I equals to close to 90 and the R less than 45. I never bigger than 80 or 90. So that is our answer. Or you can write here, if I take, this is another argument, you can write this one also. Sine I divided by sine 45, that is equal to 1.5. So here, this is only possible if the sine I value is greater than 1. And if you have studied mathematics, you must have noticed whenever you take the sine of any angle, it's never more than 1. Okay. Or a third option of writing this answer is that the sine inverse of the 1 by n, or sine inverse of 1 divided by is 41.8. So R not be more than C. It cannot be more than the critical angle. They have calculated here the critical angle. The critical angle for the glass is 41.8. So, okay, it's a little tricky question. So we are going to the next part. Okay, so the next part is here. He says the blue light traveling in the air strikes the side of a different glass block and continues in the same direction as it enters the glass block. Figure 10.2 shows the ray of light and the shape of the glass block. The critical angle for this glass is 42 degree. Explain why the light continues in the same direction as it enters the glass block. So they are basically talking about this point when the light entered into the glass block. You can see the light has not changed its path. The light has not deflected. The light has not refracted. The light has not changed its path. The reason is the light is making 90-degree angle with the surface of the glass. That means that the angle of incidence here is 90 degree, which means that the light is traveling along the normal to the surface. So if when the light enters into the glass block by moving on the normal, along the normal, the deviation do not takes place, the light do not refract. That's why the light has not changed the path. So I hope you understand what I am saying, and let me show you the written answer. So here comes the written answer. It says light entered the glass block along the normal to the surface of glass. Angle of incidence here is 0, so no refraction took place. So no refraction took place. Um, I just one thing hit my mind when I was explaining this question. I said something that the angle of incidence is 89. So when the angle of incidence will be 90 degree, I said that the light will be moving along the normal. That is not the case. When the angle of incidence will become 90 degree, the light will be moving along the surface of the glass. So when it will be moving along the surface of the glass, it will never enter into the surface of the glass. So I cannot be more than 90 for I equals to 9. Okay, so I think during description, I said that when the angle of the incidence will be 90, the light will be coming along the normal. That is not the case. If the angle of incidence becomes 90, it means that the light is traveling along the surface of the block. It is not moving along the normal. So when the angle of incidence is 90, the light will be traveling along the surface of the block, the glass block, and it will not enter into the, let me show you. Yeah, so you see this angle of incidence, if it is 89, the light will be here somewhere. If you make it 90, the angle, if you make the angle of incidence 90, the light will be traveling like this. It will be moving along the surface of the glass block. So when it's moving along the surface of the glass block, it angle of incidence will be 90. So it will not enter into the glass block. So I think I said something wrong in my description. So light enter the glass block along the normal to the surface of the glass. So angle, when the light will be moving along the normal, the angle of incidence will be 0. And what does this mean? Let me tell you that thing also, make it more clear. When the light will be moving along this is the normal. Huh? So if the light will enter here along this normal, then the angle of incidence will be 0. I, I thought that I had said something wrong. Okay, so we are done with this part. Okay. So let's move to the next part. He says, so we are done with this 2 marks question. He says, on the figure 10.2, complete the path of the light until it leaves the glass. So we have to complete this path. Okay. So let me show you. I have done this, and let me show you. So you see here, the light is entering. So I prolonged it. When it touch here, I draw a normal here with the protector. I will check how much is the angle here. I will draw, and that angle will be more than 42 when you will measure it. And so the total internal reflection will take place from here, and the light will go. The angle of incidence and the angle of reflection, here the angle of reflection, they are equal to each other. So the angle is on this side, same angle I draw here, and then I draw this. When it touch this surface, I draw normal at this point of incidence, and then I check how much is the angle of incidence here. It will be more than 42. So the process of total internal reflection will take place. So the light cannot go out. Here the reflection will take place. So whatever is this angle, same angle I will draw here, and the light will come here. So from here, then it will exit. So I hope you understand this diagram. It's a little tricky thing. So let's have a look at the marking scheme. He says the correct, the D first part is that the sine of I is equal to 0, ray enters directly along the normal perpendicular, or sine R equals to 0, no refraction. Okay, so that is that answer which we just gave. Then the light enters into the along the normal, it do not deviate. Correct reflection at the bottom suffers by I, second correct reflection at the top, and no refraction at either point. Okay, so we are done with this. So we are done with the question number 10. So we are moving to the next question. The next question coming up on your screen is question number 11. He says strontium SR 3890 is a radioactive isotope. A nucleus of strontium 90 decays by emission of beta particles. Beta particles are like electrons. Their charge is -1 and their mass number is 0. Define the term isotope. The isotopes of an atom are those atoms who have the same proton number, but their nucleon number is different from each other. Basically, isotopes have the same proton numbers in their nuclei, but they don't have the same number of neutrons in them. That's why they have different nucleon numbers. Let me show you my written answer. So here we go. So if you look at here, atoms which have the same proton number but different nucleon number are known as isotope of each other. Okay. Then the question is, let me first go to the marking scheme. He says, same element or same number of protons, atomic number, different particular number, or neutron number, or nucleon number. Remember these spellings because I always forget them. Nucleon number. Okay, so nucleon number, my spellings are right. Okay, so let's go to the next part. He says, for a neutral atom of the strontium 90 state, the number of electrons, the number of neutrons. You see, the strontium, it's 3890. So the number of electrons are 38. The number of electrons and number of protons are equal in the neutral atom, and the number of neutrons we can find by subtracting the mass number, nucleon number. From the nucleon number, you subtract the proton number, and you get the number of neutrons. So let me show you. So here we go. So the number of electrons will be equal to the number of protons because the atom is neutral. That will be 38. The number of neutrons will be 90 minus 38, and that will be 52. From the mass number, subtract the atomic number, and you get the number of neutrons in the nucleus. So you get 52 neutrons. I hope you understand. Let me show you the marking scheme. 38 and 52 is the right answer. Okay. So here we go. The next part. Sorry. The next part is a 2 marks question. He says, when a nucleus of strontium 90 decays, it becomes a nucleus of yttrium, symbol Y. Complete the equation for this decay. Okay. So here you will write -1, and on top you write 0. Here a proton number will be increased and the mass number will remain unchanged. So let me show you my written answer. Okay. So here we go. So you can see here that beta particle -1, 0, and whenever a beta decays happen, the daughter nucleus has one more proton and the mass number do not change. So it will be 3990. Hopefully you understand. Let's have a look at the marking scheme first. So it will be 3990 minus 10. So our answers are right. Okay, so we are going to the next part. He says a sample initially contains 6 expo8 atoms of strontium. The half-life of the strontium 90 is 29 years. Calculate the number of strontium-90 atoms that remain in the sample after 87 years. Okay, so it's a question on the half-life, a very simple question. And the technique by which we do these numericals is, so 6 expo 8 divided with the 2, you get 3 expo 8, divide again with the 2, you get 1.5 expo 8, again divide with the 2, you get 0.75 expo 8. So 1, 2, 3, 3 half-lives have passed. In one half-life is 29 years. In 87 years, there will be 3 half-lives. So 1, 2, and 3. So how much will be left? 7.5 expo 7 atoms of the strontium will be left. Hopefully you understand. So 7.5 expo 7, this much atoms will be left. Okay. Now the next question is, he says, describe, it's a 4 marks question. He says, describe an experiment that shows that the sample emits only beta particles. Okay. So the strategy is very simple. What you do, you take the GM tube and you check how much is the background radiation. You note it down, what is the background radiation, and then you put the sample in front of the GM tube a few centimeters away from the GM tube to make sure if the alpha particles are coming, the GM tube can detect them. Just put the GM tube few centimeters from the sample, note down what is the reading of the sample, and then put a paper between the sample and the GM tube. You will notice that there will be no change in the reading. If by putting the paper, if there is no change in the reading, that means that there is no alpha particles. When you put a paper between the sample and the detector, and the reading on the detector has not changed, it means that the sample is not giving out alpha particles, because the alpha particles cannot penetrate through the paper. Then take aluminum foil of 5 centimeter and put it between the sample and, sorry, I said 5 centimeter, 5 millimeter. Put it between the sample and the detector, and you will observe that the reading will drop down to background radiation on the GM tube, which shows that it has beta particles. There were no alpha particles. Now it shows that it has beta particles because the reading has dropped to the background radiation. That shows that there are no gamma rays, because the gamma rays, if the gamma rays were present, they cannot be stopped by the aluminum foil of 5 millimeter. So when you put aluminum foil between the sample and the detector and the reading drop down to the background radiation, that shows that there are only beta particles, no alpha particles, no gamma particles, no gamma rays. So let me show you I have written this answer, and let me show you my answer, and we will, yeah, here comes this. So this is the sample in the lead box, and here is the GM tube. So I will put a paper, then I put aluminum foil, then I can put a lead between them. So just check what I have written. Note background radiation. Place the sample in front of the GM tube a few centimeters away from the GM tube. Note reading on the GM tube. Place paper between the sample and the detector. There will be no change, which means that there are no alpha particles. Place aluminum foil of 5 millimeter thickness between the sample and the detector. Reading will fall to the background radiation. That shows that there are no gamma rays, only the beta particles are present. Hopefully you understand. So let's have a look at the marking scheme of this part. Here he says detector, detection film for, okay, solid. You can use a detector. And here is the marking scheme of this part. So the marking scheme, no reduction with the paper, complete reduction with the aluminum or lead. So this is what I have written there. So you can take your time, you can pause the video and you can check this answer. It's a 4 marks question. Very important question. And the answer which we have written is perfect. Okay, so we are moving to the next part, which is the last part of this paper. He says, our teacher says that emission of the beta particles from strontium-90 is random. explain what is meant by random in this context. And then he says, state two ways in which the emission of beta particles from strontium-90 is random. You see, random, both the parts have the same answer. What is meant by random? Random means that you cannot predict that which atom of the strontium will decay. You cannot predict at what time it will decay. You cannot predict at what time the decay will happen. You cannot predict that which atom will decay. Then he says, state two ways in which the emission of the beta particles from the strontium is random. You cannot predict that the beta particle will come from which atom, and you cannot predict that at what time a certain atom will give out beta particle. A little tricky thing, a little tricky thing. Both answers are exactly the same answer. Okay. He says, we cannot predict which atom will decay. We cannot predict when an atom will decay. And we cannot predict time delay between emissions and cannot predict which atom will decay and give out you the beta particle. So I think this is done. Okay, so let me check the marking scheme. So the marking scheme for the first part and the second part, both are showing up on your screen. You can pause the video and you can check the marking scheme. So my dear students, today, my dear students, today we have done October, November 2014 2 paper, and in this video, in this session, we have done the section B of this paper. The section A of this paper I have already done and is uploaded in my YouTube channel in the same playlist. Above this video, you can find the link of that video. In that playlist, paper 2, zone 2, in the past paper practice of the physics 5054. So if you find this video interesting, informative, and helping to you, please share the link of this video onto your Facebook account, onto your Twitter accounts, onto your Instagram, and also in your Google Classroom. Share the link of this video through the WhatsApp with your friends and with your junior students. So when they come, when they prepare for their assessments or mocks or their upcoming Cambridge exam, they can benefit from these videos. Also subscribe my channel because and also comment on this video. So my dear students, your appreciation is fuel for me. It's a great pleasure for me to teach you online. So thank you very much, everybody. Everyone who is watching these videos, everyone who is working to prepare for the Cambridge exam. Thank you very much for watching this video, for taking out that time and providing me an opportunity to teach you online. So thank you very much. It's a pleasure for me. God bless you all.